The next talk is by Alex Kontorovich, and in his talk, Leo told us on Monday that there were surprisingly many courses using Lean around the world, but actually we got only one submission about teaching with Lean, and we are very happy to have that topic at the conference. So, Alex, the floor is yours,
Thank you very much. I'm not sure if I'm allowed to invite people
and we
to
don't hear
interrupt
you,
during
or
the
at least I
talk.
don't.
And oh, can you hear me? Do you hear me or no?
Oh, sorry, I think it was on my
Yes.
side. Yeah.
Okay. I wasn't sure if I was allowed to invite people to ask questions during the talk or not.
Yeah, sure.
Okay, there's no rule against that. Yeah, so please interrupt at any time. Thanks again for the invitation and the opportunity to speak here. It's a great pleasure and honor, of course, always to be with the community. Yeah, so let me tell you about this real analysis game. So in the end, there were 44 worlds, 138 levels. You can go play the game yourself. It's on the server. And I just thought I would tell you some of the ideas and things that came up in the process of teaching this and how it came to be. So this was taught last fall. I mean, this past fall. Obviously, it's inspired by Buzzard's by a popular natural number game. It started out with me just trying to figure out, is this even remotely within the realm of possibility? I'm not a coder. I'm not. I'm in awe of people who have all these skills. I just, do math on the blackboard, and so this was a big challenge for me. But enough hours iterating with Claude that I could kind of get started convinced me that there was a chance that I could make it work. And then John Euxter was extremely helpful in getting it actually set up properly and getting it to run and so on so that it could work. Of course, I got a lot of help from lots and lots of people, especially want to say thank you to Heather, Mikhail, and Dan Vellman, and the students in the course, and lots of people who contributed dozens of PRs and issues since then. And it seems to be something that I'm going to spend a little bit of time working on. So let me tell you about the course structure just to lay the groundwork of how everything happened. So it was just a regular course, 2 80-minute lectures a week, one recitation that was run by my PhD student, Maddie Krim. This was just an honors section of our real analysis course. We have, I don't know how many, 10 sections or something. One of them is the honors section. These students did not sign up for Lean. Okay, so this was not sort of a voluntary, oh, yes, I would like to learn Lean. Please teach me how to do it. No, no. They want to learn real analysis. And unfortunately, they're stuck with me at the front of the classroom. So it was an experience for all of us. If you want to follow along, I tried to document everything in this experiment. So all the lectures are recorded, all the notes and the videos are posted. The notes are posted to the GitHub page that you can reach from, there's the main course webpage on the main game page, and it has all of the lectures that are posted to YouTube. So watch the whole thing, see all the good and the bad that happened. Um, the way I eventually figured out a, a better way than what I was doing at first was to handwrite everything. So I walked in with a stylus, I would open up the game, we would see what the goal was, and basically would put the game away and just talk about it by hand. And by hand means we would be sort of sketching out a proof and then eventually writing out a formal proof by hand. And then when we were done with that and we'd convinced ourselves that we had a formal proof, that's when we would go to the game and just plug it in and check that everything that we thought works the way we wanted it to. Okay, so that was roughly the protocol. The topics that we covered, so there were 25 lectures in all. It was not so far off of what a standard real analysis course should have been. I would have liked to hit power series if there was time, Fourier series. But overall, I think we covered a broad range of topics. We did step on the gas, admittedly, at the end to hit these. But I think that in terms of the other thing that taking a course in real analysis is supposed to teach, namely how to think about theorem proving, if not write and communicate theorem proving, but at least how to think about theorem proving. I think in that sense, it actually did better than a typical such course. Maybe that's because this was the honors section. There's a lot more experimentation that needs to happen before we understand whether this really works or doesn't work. Okay. Um, so these are the topics. I won't go through them. Not everyone here is even a mathematician, so it maybe doesn't make sense. I will make some comments, some particular comments about the mathematics later, because there are some interesting things that happen mathematically. The theorems were the tactics and the definitions you can click through yourself. The theorems I bucketed into sequences, which is just AN, series, summation AN, things about absolute values that hopefully in the future will not need to exist, things about functions, things about integrals, and things about topology, and then some general theorems and so on. So this was the rough decomposition of the topics. The homework was assigned in the game. So you can see lecture 9 goes to problem set 9, and then problem set 9 isn't due until after lecture 10 happens. So we don't use the mathematics in problem set 9 until lecture 11 and so on. So you get this kind of funny crisscross pattern in the dependency graph of the games. Each lecture was prepared just in time, sometimes literally just in time. And Oliver Nash can speak to that because he was sitting here in my office about a half hour before I was running off to teach. And I was still furiously trying to figure out how to make something work that just was not working. And yeah, so a lot of time it was not the hour before the course, but staying up until 3 or 4 a.m., unfortunately, the night before lecture to figure out how do we get this concept that is so easy to explain in natural language to actually work and work within the game and work. It's not that it has to be provable in Lean. All of these things are provable in Lean. How do you prove it in Lean in such a way that you can explain it to students who are not Lean experts, who only have the tools that you've given them so far, and I have to introduce the tools one by one. I can't throw 3 new tactics at them in one lecture and expect them to be able to follow along without losing the mathematics, right? The mathematics has to be the core of what's going on. The evaluations were 2 timed in-class midterms on paper, just pen and paper, and a final exam again on pen and paper. And I'll say more about that later. Okay, so again, students did not ask to learn Lean. They were promised real analysis, and so every design decision had to be, I'm going to try my best to meet the students where they are. So obviously, we're not going to use filters. We're going to use lots of non-mathlib definitions, and in fact, quite not a good amount of the time, I had to invent new definitions for things that I thought I understood. You know, I took real analysis a quarter century ago or something like that, more than a quarter century ago, and so I thought I understood these things, but it turns out that there's always a deeper, a better way of thinking about it. So the definition of sequential limit is exactly the first thing that you would write down. The definition of compactness, my experience was that this was a better definition of compactness than the definition that I know. And the only difference between this definition and the standard one is that we don't have cover by arbitrary open sets, but by open balls. And the type is an indexing type that tells you where the base points are and what the radii are of those open balls. And then you have your set. The fact that the set is compact is that if it's covered by these open balls, then there exists a finite subset of the indexing set so that S is also covered by balls. It's equivalent to the standard definition of just arbitrary open sets, but it turns out that for at least the way I was doing it, it was important to be able to say, okay, take this ball and have access to the center and the radius without needing to go to open balls and get a neighborhood around every point in the open set. So this actually ended up simplifying a lot of the calculations, and it's an equivalent definition, so why wouldn't I use it? There are a lot of things like that. I'll highlight some of them, but I probably won't have time for all of them. Okay, so more pedagogical techniques. Any questions so far? Maybe I'm going too fast, but I want to get through
I'll,
some things.
I'll jump
Yeah,
ahead and ask the question if you don't mind.
please.
And I'm sure you're probably getting to this. How is this received? Did the students like this?
Right. Let me, can you ask that question in 10 minutes? I do want to get to it because it's a highly non-trivial question and the answer is subtle. I see
You could
another
have
hand.
you could
One
have
question.
defined.
Oh,
Sorry, go on.
Go ahead, John.
The question is, but when I was messing around with real analysis for students, how did you handle the product algebraic limit theorem for sequences? Is that theorem the same? Is the proof the same as what you do in an ordinary linear analysis course now? Or do you have to do the one that Kevin has put up, the more complicated one that's more lean friendly?
No, we do the standard proof, but there are a lot of prerequisites that have to go into that proof.
Wait, what's the standard proof?
I mean,
But
add zero, and bound things and stuff. And
You have to bound things. Yeah, you have to bound
yeah,
things away from zero.
right.
oh boy. Yeah, so there's this proof that Patrick told me where you prove the product of two things that tend to zero tends to zero, and then you
Yeah.
deduce the general case by shifting.
Yeah, that's pretty
which
good
I
too.
thought was very beautiful.
It's lovely. That
Uh,
works.
Sure. That works too. Yeah, we do separately. I mean, there's always a decision about where you split things, but we split it in. We have a separate proof that if you have a bounded sequence times a sequence going to zero, that product goes to zero. That's a very easy thing to prove. And now you don't need that both of them are going to zero. Just one of them needs to go to zero. And then that you can hook up. Anyway, you can see what's in the game.
It's
Um,
nice. It's nice.
yeah.
Thank you.
So there are a lot of things like this, and maybe I'll get to. I'll say a couple of them, but yeah, just want to make sure I'm not going too fast and sort of running away with the ideas. Please interrupt at any time. Okay, so other pedagogical techniques and ideas. One was that because I had in mind that people who aren't in my lecture would want to play this game, I don't want to just give them the game because I know how everybody works. I know how I work. When I played the natural number game, I didn't read the thing on the left-hand side until I actually got stuck somewhere. Right? You look right in the middle. The middle is the game. You just start playing the game. You don't want to read. Uh, I do math because I don't want to read. Right? Isn't that how it works? And so I did put up sort of a story time that starts a lot of the lectures, especially when there are really subtle things. I mean, real analysis is full of things that you teach in one semester, but they were discovered over centuries of people really struggling with deep mathematical issues. And so I came up with this. I like a Socratic dialogue kind of thing. So I use this Socrates and Simplicio conversation to introduce the more subtle things, and then when we didn't need them, they were out of the way. But really, people don't want to read. Um, every solution anytime we solved a problem, it had to be a problem. And so if you read any textbook on real analysis, chapter one is the construction of the real numbers or some version of it. You know, the nested intervals property or the least upper bound property, whatever property you're going to start with in order to deal with the real numbers. And I remember as a kid, we spent the first 2 weeks of real analysis constructing the real numbers. And then and I was like, I know what the real numbers are. I've been using the real numbers since, second grade. It's like, here they are. And then on week three, we forgot all about those first 2 weeks, and the real numbers went back to this. And I'm like, so what the hell was that about? What purpose did that serve? And so I said, forget it. You know what the real numbers are. We're going to start immediately with sequences and series. And at some point, there's going to be something subtle where we're like, wait a second. Why is this true for reals and not rationals? And that's the point where you need to start introducing what the real numbers actually are. And so that came at the proof of Bolzano-Weierstrass, and that was the point where we started talking about the need for that. Again, in most textbooks, they're going to introduce topology before they go to things like, well, does a Riemann sum actually converge to an integral and continuity versus uniform continuity and these kinds of things. You need topology in order to be able to do it, but I don't want, this is a course on real analysis. What the hell are we doing topology for? I'm not ready for that. And so the way I backed into topology was by first proving the things that I could. A Riemann sum converges if the function is uniformly continuous. Well, when is it uniformly continuous? It's uniformly continuous if it's continuous on a compact set. Now we need compactness. What does it mean? What does it mean to be compact? And now you get the Heine-Borel. So everything is kind of backwards from the way it would be done, the way it is done in MATLib. And most textbooks are trying to write MATLib. But MATLib already exists. And I have the freedom to just teach it basically in the way that it was discovered, actually, much closer to how mathematicians came up with it. And so the rule was always, you don't solve a problem until it's a problem. We have to know what we're doing. Why we're introducing topology at this point in the course is because we want to know that Riemann sums converge to Riemann integrals. So there's always an application that's driving the conversation. Okay, so these are, again, in the wrong order if you're actually constructing things from scratch, but they're in the right order if that's how you want to learn them, and we try to build everything just in time. So speaking of Bolzano-Weierstrass, this is one of the things, I mean, there are many things like this, but I just want to highlight this one in particular. The standard statement that I've known for a quarter century is wrong. It's not wrong in the sense that it's not true, but there's a better statement that's true. And Bolzano-Weierstrass should not be if you have a bounded sequence that has a convergent subsequence. What it should be is if you have a bounded sequence, then there's a subsequence that's Cauchy. And that statement is true if the sequence is a sequence of rational numbers. And that's the point where we introduce the real numbers as equivalence classes of Cauchy sequences. But now you've seen Cauchy sequences for a while. You have a lot of experience with Cauchy sequences, so they're not something out of the blue. And you realize that's the way to do it. And even the proof is nicer than the standard proof. I mean, think about the standard proof. Let's say you have a sequence bounded between 0 and 1. Okay, so the standard proof is you bisect and you look at 0 to a half versus a half to 1, and one of those has infinitely many points in the sequence. And iterate. Done. QED. Right? That's it. That's the natural language proof. This can be done in Lean, but the amount of technicalities that it introduces to execute this induction is non-trivial. Whereas a very, very easy thing to do is to show that if you have a monotonic sequence and it's bounded, then it's Cauchy, and same thing for antitonic sequence. And then every sequence, and this is not about subsequences. The sequence itself is Cauchy. If it's monotonic and bounded, then it's Cauchy. And every sequence has a subsequence, which is either monotonic or antitonic, monotonic increasing or decreasing. Okay, so it's an easier proof of a stronger theorem. Why isn't this in the literature? Because you never needed it in the literature, because this explanation is a perfect explanation in natural language. Okay, so these are the kinds of things you learn when you force yourself to teach formally.
So if you don't mind me asking, was this like a general feature? Like, did you often find, oh, the natural language proof is one thing, and we just have to change it completely? But maybe it's still nice. I mean, it seems like you also tried to make whatever you wound up with nice and understandable, as opposed to just some crazy formal, mess.
Yeah, well, basically what would happen is until 2 a.m., I would be still fighting with Lean to try to get the natural language theorem to work. And then for the next hour, I'd be like, okay, start over. I know what the theorem is. There's got to be another proof. And then I figure out another proof. And then I realize, oh, that proof is just butter in Lean. It just goes. And so that's at 4 a.m. I would go to bed uh, and teach the next morning. So this
So
I didn't set out to rewrite real analysis. But that's what happens when you start teaching something, especially if you're trying not to teach Lean. I'm not trying to teach Lean. I'm trying to teach real analysis. So as many of the Lean things need to be out of the way. Uh, yeah, as Patrick says, the entire field
right.
is full of this kind of exposition changes that only arise when you're formalizing.
So did you find that this went hand in hand with your changing of the definitions you mentioned earlier, where you'd be like, oh, well, I have this other proof, and it's better if I have this definition. You kind of work backwards the definition, or
I
was it just like,
started with this, yeah, exactly right. I started with the standard definition of compactness, and I proved a couple of theorems, and it was like a real slog because I constantly had to go back from, I have an open ball, but I need a point in that ball, and where is it? And the balls contain open sets. Just give me the ball. I'm like, wait a second, can't I just make compactness the ball? And then I don't have to worry about it. I'm already indexing the centers and the radii.
I mean, you could define compactness the usual way and then prove it's equivalent to the ball definition, and
That's
then just keep
right.
applying that theorem.
You absolutely could, but it was easier to invert it the other way and give the definition in terms of balls and then prove that it's equivalent to the standard one with opens, it turns out. At least that was my experience. And all of this uh, was an experiment. And so I invite lots and lots of criticism and suggestions for better ways to do things. Um, okay, so right, here's another thing, just for one more example of something that's just completely obvious and doesn't require another word in natural language. You have some property, and that property holds infinitely often. For every integer, there's some integer after that integer so that the property holds. So then there's a subsequence. Subsequence is my word for strictly increasing uh, sequence, a map from the naturals to the naturals, so that sequence always holds along this subsequence. This property always holds along the subsequence. Do you know how to construct such a thing in Lean? Is it obvious to you? I had to think about it for a few
Recursively,
minutes. What's that?
recursively.
Yes, recursively, but how recursively? It turns out it's a very, very simple and completely natural construction, but I don't know of a single book where this is written down. You just take the orbit. So you choose, the fact that this exists for all n means there's a function that sends n to the thing, it sends capital N to the little n for which the property holds, and then you just iterate that n times. That's the recursion. It's an orbit. It's the most natural thing in mathematics. It should be in every textbook. I opened up 100 textbooks looking for it. I found it nowhere. I do not claim that any of this is original, okay? It's just my lack of understanding of every math textbook that's ever been written, but I don't see this. And it makes life so easy once you introduce just a couple of key ideas. All right. Some more design decisions. Okay, so we're currently working with a lot of help from Jason Reed and Emilio Ares, to whom I'm grateful, on a version that instead of writing in text, you do it like Scratch, like the MIT coding thing where you just drag tactics and drag variables. Over here is going to be the info view. This is the debugging version where we're just figuring out how it's interacting with Lean under the hood. So that will take us from version 0.1 to version 1.0. And the point and click thing would be amazing to plug into that. And a couple other things. So we didn't have calc blocks, and I substituted. I was perfectly fine without calc blocks because all I did was linearith instead of calc blocks. You just say what all the statements of the calc would have been, and then linearith them together. But I didn't want them to have the power to just say linearith and say, I hope it works out. I hope I've thrown enough things in there. So I weakened, just like rewrite in Kevin's game is weakened to RW is weakened to rewrite. My linearith was weakened to linearith only. So they had to specify which hypotheses they were putting together in the final linearith. Casting was extremely painful. I think we now have tactics that are a lot better than the tactics that I was using at the time. But for example, this is the proof that -1 to the n does not converge. And it's just a real slog to get through all the various things you have to do with casting. And does bound do this or does norm num do that? I need to figure out a better way of hiding which tactics do and do not do what I want them to do. Okay. As I learned from Heather, I don't want theorem names. As much as possible, I only want to call tactics and not know, oh, this is the theorem that tells you that the absolute value splits up, or this is the theorem that says that you can switch, you can negate and inside the absolute value. So coercions and casts, do they affect playability of the game? I think they do. I think coercions and casts make it much harder to play the game, and we should have better tactics to be able to see through that. Like it'll know, we'll have in the info view that n as a natural number is less than capital N, and then for some reason it's not picking that up when I apply bound or something. But if I then add n cast into the reals is less than capital N cast into the reals by exact my cast, all of a sudden a tactic will work. So there are ways to get around this. I just, because I was doing everything just in time, I didn't have time to get the tactics to work exactly how they should. Here's another thing. When I gave them intro, I showed that intro works for both epsilon and the hypothesis on epsilon. And they were confused. They're like, why is that? That's weird. We break up objects, we break up the info view into objects and assumptions. Right? Precisely because people think of these two things as different. I don't want to have a conversation about Curry Howard. That's not that's not the time for it. But they're inviting that conversation by having one tactic that does two things that seem different. So I learned from Dan that you split intro into you fix epsilon, and you assume that epsilon's positive. And in the same way, I'm going to get rid of specialize. You plug in the name of the variable, and you feed in a proof. It's just a layer over intro and specialize. But for people, they think of objects and assumptions as different things. That's already built into the game. So the tactics should reflect that. And then once you're in a few levels and you say, you know how it's annoying you have to write fix and then assume? Let's just make one tactic that does them both. And we pretend that it wasn't engineered the other way around. The other thing is no naked tactics. So this is something that I observed, so I gave them that x squared plus y squared is 2 and that x times y is 1, and I wanted them to prove that x plus y quantity squared is 4. You hit it with ring, and you don't know what the answer is going to be. You don't have control over the outcome. So I said, no naked tactics. If you want to apply ring, you have to say exactly what ring, unless you're closing the goal, you have to say exactly what that ring is supposed to do. Now you have control. If you get down to here, now you have to really struggle to make this look like something that you can rewrite. Like you can't rewrite H2 because it's x times y times 2. So it's not going to see x times y. Stuff like this, okay, which is really, really painful, really annoying. How did the students react to these tricks where one had to massage tactics? Well, this is part of the pain, is that I didn't realize some of this stuff until, the week after I introduced it to the students, and we struggled, and I was like, okay, wait, here's a better way to do it. So everything was... so you asked about how students liked it. So this is my graph of the students accepting the curve over time. So it starts out over here. I would say about 30% of them liked the idea of doing lean. The vast majority were there to do math. And then when we got a little bit into the course, I think it went up. And then we got to casting, and it would drop to maybe about 10%. And then we got used to casting more and more, and I would say ended around about 70% acceptance. So I would call that a win, but it was definitely like there's a period where we're getting better and better at it. Then all the casting issues and frustrate us, and we're down to 10%. And then there's like one guy holding out who's a diehard lean fan who still wants to do this. And then I would say we ended up overall people were okay with this. It was not a complete failure. Um, okay, so let me try to make sure I get to the end with enough time. I spent quite a bit of time trying to see if I could make Patrick's amazing verbose lean work in with the game. And again, I was already in over my head in terms of coding chops, just making a game in the first place, and then to combine that with this verbose, I think would have been too much at once. My mistake is doing examples. I think you're right, but I had to. Without the examples, that's where casting appears. I agree. Um, uh, I had to do examples. I'm sorry. I had to. I can't explain. The first thing we're going to prove is 1 over n goes to 0 as n goes to infinity. We have to do it, and it was a nightmare. Um, right. So there were two things. A, I was worried I wouldn't remember what the controlled patterns, the controlled language patterns were because I didn't make them up. And B, I was sure I wouldn't be able to do the coding. So, if we're writing in natural language, you're really free to say whatever you want. If you're writing in Lean, there are very, very explicit rules for what to say. And for both, I was worried that it made me feel like I could write freely, but really I can't, right? It's actually controlled natural language. That said, there's a shift click to make sub expressions and so on. It's a beautiful system, but actually the fact that I didn't use it made something else happen. So by the end of the course, I realized I don't want to teach people to prove natural language anymore. That was the kind of big realization. Let me explain. On the final exam, I didn't have an example from the final exam because I didn't take scans of the final exam because I didn't give those back, but I gave back the midterm, so I scanned the good solutions on the midterm. Who's boss? Yeah. Uh, so this is just what it looks like when the students are writing out the formal proof by hand, and they're supposed to keep track off to the side. What you don't see is the student keeping track of how the goal state is changing. Not the entire goal state every time, but just this is the key thing what is HN1? The student wrote down over here uh, what that said. So there were examples, especially in the final exam, where they had the option to write the solution in natural language or in formal language. And many of them chose to write formally. They just saw it as a better way of writing things. And so it occurred to me, okay, now I finally understand what's going on. In the 16th century, you did a lot of algebra, and this is how you did it. You have an unknown quantity, you create a second copy of the quantity, you combine it with an unknown amount, multiply that by your original, and get the specified result. And today, with training, with a significant amount of training, it's much faster, much easier, much more precise to just write x times x plus a equals b. And these two things are the same. Okay? So that's my claim, is that 100 years from now, it took a century for this to turn into that. And I'm unapologetic about not using natural language proofs because I actually think we should stop doing that. And we should start proving things in the 21st century. Okay, so thank you for your time.